Hello everyone. So welcome to this session on the continuation of the series on deep foundation models. So our discussion in the last session talked about transformers architectures related to the construction of a transformer model, self-attention and some level of self-supervision tasks. So today we will continue the discussion into large language models, both input and output side, which involve tokenizer and sampling, as well as on the pre-training as well as post-training approaches that are used. In particular, we'll spend some time on reinforcement learning based fine-tuning of large language models. So just a reminder, so some of you may not have attended the previous session, some of you have attended, but it is still good to lay the scope out. So we are going to do a bit of breadth-wise search. We are going to cover a bit of topics on the breadth side and at the expense of going too deep on some subset of the topics, right? A part of why the motivation for certain topics will get discussed, and in addition to that, where they get applied, I try to put that perspective with you so that you can now link with various other things that you may read online, that you may be using online as tools. You can probably get a little bit of feeler of what goes under the hood and many of these models and frameworks. So what is not covered? So what is not covered, of course, is a lot of the math, right? A lot of the underlying background that has propelled, and some of them go back decades of mathematical foundations that have propelled these methods. And the details, including the algorithmic implementation, the hacks, the engineering tricks, the key frameworks to make them all operational such that they actually run at scale, run at the speed that we want them to run at, those things will also partially get omitted out of these lectures.
Recording in progress. Recording stopped.
So now, on top of all this, this is a bias sampling, right? This is essentially a set of topics that I chose, right? Partially being the presenter, I get to bias the presentation, right? But it doesn't mean that the coverage of the topics is anywhere close to comprehensive or exhaustive. Lots of topics. In fact, making many of these presentations, the hard task was not to put the slides together. The hard task was to omit what all I should not be talking, what all I should avoid, so that we have a small subset of topics, right? The area is very vast, evolving. Some of the things that I am going to say are already old. By the time you go out and read the current literature, you will start seeing that some of the things that we discuss are already 2 to 3, if not 5 years old, and the technology, with every conference, with every passing month and fortnight, things are evolving. Right. So with that caveat, with that small disclaimer, I'm going to get started. And of course, I have used many of the topics that we are talking about, the derivatives of those topics being ChatGPT or a Gemini. I have extensively used them for these slides also, right? It's now become a circular loop that way. All right. So what is this lecture about, right? So this lecture, we are primarily going to focus on the topics that are listed here. Some subset of the topics that I listed are not included in this, particularly to keep the time alongside the consideration, and they will get picked up hopefully in the next session that I will put together. So what we will cover today, though, is going to be on large language models, primarily the input and the output side. So we talked a lot about what goes into the core of the transformer architecture, core of the self-attention modules, core of the positional encoding and other things in the last week. So now we are going to put that core into practice with various other ingredients coming together. Then we'll talk a little bit about multimodal models, multimodal alignment. Then the second half, the subsequent part of this lecture, will go into pre-training, making these architectures, modeling techniques and algorithms to use for various downstream tasks. In particular, we will spend good amount of time on the reinforcement learning side. Again, the derivations and all those will be left out. We are going to be very light in our coverage, but this is just to prop the interest, and hopefully you are all going to pick it up if you are going to work on this, or for your interest to know what goes more deeply into this. Hopefully this is the opener for that. So let us get started with the first topic, which is on the LLMs and particularly the input and output side. So just a reminder, just as we said what are transformers, now we can ask an LLM itself what it thinks of an LLM, meaning a circular loop again, right? We are asking an LLM itself who are you, right? In this case a chat GPT, I am asking who are you, the chat GPT says this is who I am, which is to say that I am an AI system trained on massive amounts of text and maybe other modalities of data. I am fundamentally a deep neural network, particularly with a transformer architecture, and now I can perform a wide variety of tasks. Right? When I said I, the model didn't say I, it generally said about large language models. Okay, so this is basically the core derivative of many of these things that you see outside, right, which has drawn this success and that essentially hype around all these LLMs. This is basically the very large, a 30,000 feet bird's eye view of what these models are. Now let's dig a little deeper, right? So again, a little bit more zoomed in version, right? So what we already covered in the previous session is again listed here. So this is the primarily the transformer architecture. But what goes into the transformer architecture, as you can see here, is a set of blocks that take, I'm going to drive a bunch of these motivations again from text and then extend them potentially to other modalities, because this is how the evolution of LLMs also has happened, that everything, let us say, drew the attention from the text world and then got extended to many other modalities. So we are also going to follow that route. And therefore, we are going to say that the terminologies that we use are also going to be, some of them grounded in NLP and so forth. So a tokenizer, which we are going to talk a bit more in detail, is essentially something that converts your raw piece of text, right, or raw piece of multimodal data into model ingestible form, right. So an embedding matrix and then a set of transformer stack. So this is basically the core that we discussed in the previous class, previous session on attention, on feed forward and so forth. And finally, we'll also spend some time on discussing the aspects at the output end. What are these transformer outputs going to come out as? What are the sampling methods to get multiple outputs from the same, let's say, input? Right. So all these parts are going to be in the initial LLM big picture subset. So again, just a reminder, this is basically the chunk that we discussed in the previous session that had a self-attention, a normalization, a feed forward, and another normalization layer, what we called as a single block of transformer architecture, right. One more point I want to remind, just for completion of this particular recap of the previous session, we are talking about decoder only models, which fundamentally means all the models that we are going to cover today would involve an input, and the model's task is to continue the input, is to continue the prediction of the same token sequence in a autoregressive setting, right. This is the LLM world where you have the decoder only models which perform the next prediction, next token prediction task. Okay, so now let's talk about this fundamental tokenizer part, right. This is again a very light introduction to tokenizer, but this is something to keep in mind even when we talk about multimodal inputs. So what are tokens, right? So we have been using, even from the last lecture, the term tokenizer in a loose sense. Now let's start grounding it. So a tokenizer is something that converts things into tokens, and now we are starting to talk about what is a token. A token, particularly when you talk about text or natural language processing, is the basic unit. This is the smallest unit that you are going to represent as a single vector, right. You are going to essentially now consider any piece of text like this sentence here as a sequence of vectors, and each vector represents a token, right. So now, how many bits, how many pieces of text? So as we know, as humans, we deal with characters, with symbols like phonemes and graphemes, alphabets as our basic unit. But does the model have to go and represent every alphabet by itself, or does the model represent text in a different form than what we as humans have learned and consumed, right? So turns out that you can do some sort of data driven modeling of fundamental units for efficiency of representations. So instead of modeling, let us say, alphabets, characters, your ASCII string or Unicode string, in the modeling world, they do, the tokenizer world, you can model whole words, you can model subwords or punctuation, special symbols. More and more increasingly, if you have also followed just the consumption of the ChatGPT style models, initial models did not have anything for emojis. More and more you see that models now output emojis, special symbols, characters, multilingual outputs, then multimodal outputs and so forth. So these are all fundamentally strings of so-called tokens, and this token world is where we are going to start off for the text. So the last example that you see, which says, I am a student of machine learning, each color here is supposed to represent a token. Okay, so the I could be one token, then the word could be, am could be another token. But if you say something like a student got broken into two tokens, then the rest of the words could be one token. So these are all potential ways in which this come out. Now you can ask me, like, how does one decide what gets to be a token? Should I put I, which is just a single character, also a word, as a token, or should I put I and a space as a token? And then if I want to say further, if I want to say I space am together as a token. So there are different possibilities in which to break this piece of text into the subparts. The question then is, how do we do it, right? Do I want to use English language skills, English lexical skills to put the use and say that this is the dictionary of words, this is the dictionary of bigram words, meaning a combination of two words and so forth, and come up with a way of segmenting it? Or should we not even go into just the English? We want to be much more generic than that, much more data driven than that. So the algorithm, that is, again, I'm going to pick the most common one to break text into tokens, the tokenizer one that we are going to talk about. I'm just focusing on the last part of this. The method is called byte-pair encoding. Okay, so we are going to talk a lot about the BPE part in the next few slides. But what are the key aspects of this? This is fundamentally a data-driven approach. Right? You are not focusing on any rules, any prior knowledge of particular language, particular setting of an image or audio or other multimodal data. You are not setting up anything that is common use in this. We want to go to a scenario where every token is not going to be fixed in length. Right? The unit, it could be text, unit could be image and whatnot, but we don't want to have these single units being single characters or alphabets. We want them to be variable in length, right? And often, if you ask most of these recent language models, in English, what is the average token length in terms of characters? They turn out to be about 4 to 5 characters. Right? So if you have about 100 characters, then it's roughly about 20 to 25 tokens is where the number of units that get mapped to the corresponding characters. So why do we want to do it is, we also want to be able to represent rare words, something that you have never seen, right? So if you take particularly any language model, right, anything that has come particularly from non-Indian settings, you ask them what is the token length in English, it will be 4 to 5 characters. You ask the question, what is the token length in Tamil? It will be 1 to 2 characters or even less. Right? What it means is, text, although you have represented multilingually, whatever is the dominant representation in that text tends to dominate also the tokenization policies, tends to dominate the token length priorities. So which also means that you are operating at a much finer scale. You are far away from semantic modeling in English compared to other languages, other modalities. So many of the things we talk about that, in text things are very good, but in audio, in images, in other languages outside English, things are not so good. Some of that can also be attributed to what is it that the model is ingesting, which is a token sequence which is biased by the data that was used to train that tokenizer. Okay. So with that caveat, so I'm going to turn back the page to about 30 years plus ago, which at that time was a new algorithm, which now is a well-known algorithm called the BPE. Okay, this is basically coming from text data compression world. We will just outline very quickly how it is done. I'm not going to give the code to run it, but should not be very difficult to write also. So what are we talking about? So we are talking about this method called Byte-pair encoding or BPE. So the goal, let's state one more time, which is to take any piece of text and represent it as a sequence of tokens, right? So any piece of text can now be represented as a series of tokens. What we also desire as a property is the frequent words, frequent sequence of characters or entities in the text should have smaller length in the token world, right? So it has to be based on the probability of a particular sequence appearing in the text, which has to get compressed into smaller units. So some of you may have done other compression methods, have seen or learned in communication or in data compression courses, for example, arithmetic coding and so forth, that explicitly use probability distributions to find the token allocation or the sequence allocation or bit allocation in those cases, right? So you want the most frequent unit to occupy the least number of bytes, right? That's the way in which even this is also expressed. On the other hand, you also want to allow every small possible entity to also be present in your vocabulary. What do I mean by that? I want to have even Unicode character entries, so that if I have not encountered a new language that I have never seen, I still have the capacity to generate them, although they are going to be in a sequence of strings that is very core or very basic to the computer representation of those linguistic units, right? But still you want to go all the way up to a single byte, a Unicode byte level, so that now you can compose them to generate pretty much anything in terms of a text world. Okay, so the overall, the assumption is you want to be certainly more efficient than the average character level representation for typical text, right? So what do we do to do this? To train, to have a corpus. In this case, I'm taking a lot of text, but you can also extend it to multimodal units and so forth. And then you decide on a set of initial vocabulary. So in English, this could be characters. You can easily think of Unicode entries as your initial vocabulary, and then iteratively refine and get adjacent symbols and token units. So let us just quickly see an example so that this is established. So suppose I had, and I have created again a biased example so that this is relatively easy for me to showcase. Suppose I have a set of words. Let's say each word here is some sort of a textual entry, say low, lower, lowest, slow, slower, etc. If I want to represent them, all of them as single characters, right, including the space that you have for every word, so the total count turns out to be 29. So if I just represent every character as a token, I have to spend 29 tokens to represent these 5 words with their space or end of the word, right? So I can now start taking this and start doing some sort of pairing. That's the term the Byte-pair comes in. Let us say you pair L and O because that is the pair that has the highest number of occurrences. So you start picking pairs, which is the one that has the highest occurrence in your data set. You assign a single token for that. Right? Now LO became a token. Now you can start seeing the word low became just 3 tokens because LO is a single token, W is the next token, end of word is the third token, and so on and so on. And if you now start making the count, it already became 20% lesser, right? Or around 20% lesser. What do? Of course, we know to do it once, then certainly we can do it more than once. Now LO became a token, now you can start pairing that token with anything else and now start repeating the process. Maybe LO and W is the next highest occurring pair, right? So you pick that pair, assign that as a token, and now the overall token length reduces, right? So you can keep repeating this, right, till the cows come home, or you say that, okay, I have reached the maximum number of tokens that I want. I don't want to go any further. You have said that I can accommodate at the most, in your language model, you say I can accommodate at the most 50,000 tokens. So then you say that you keep merging this till you have reached 50,000, right? So some animation got messed up, but the same procedure can be repeated to any discrete sequence. We showed it with text, right? But let us say your image, which was patched and had representations in terms of a code book. Last week we discussed about VIT as a encoder for images, and then how you can take patches of images and then convert them to a discrete sequence. We also talked about audio. So fundamentally they are all coming up with, let's say, codebook entries, but you can now make pairs of codebook entries to become your token. So in that case, what happens is you're not trying to model a single patch of image by itself, you are trying to model them as more larger units of image, right, or larger units in the audio world. You are not processing every 20 millisecond as a single chunk of audio, you are looking at longer units because they are fundamentally repeating more often, so you have assigned them to a single code book, right. So the more the data, more the representation of certain regularities in the data, the larger the unit becomes in the modeling world, the more semantic the model becomes, right? Because you have moved away from, let us say, L, O, and W being separate entities to the word low or to the word slow and so forth. Now they become meaningful. Now they have semantic components attached to when you combine these tokens. So now the model also operates in a more semantic world than the pure refined character level world, right? So that much is largely what I want to cover about tokenizer. Of course, there is a lot more other approaches, but what we discussed is perhaps the most common one. And many times when you see, let's say, your versions of models coming out, let me just finish this. When we see versions of models coming out, right, you have, let us say, very recently or yesterday or the last week, Gemini 3 got announced. And suddenly you say it has much more newer capabilities, much more newer language support and so forth. Fundamentally, what has happened? Of course, training data has increased, but the tokenizer has also changed, right? You start with the core of it. The tokenizer first change would make a deep impact in representing new languages, new domains, new modalities, that now you can start fundamentally semantic modeling, right? Previously you used to feel, right, if you write in Hindi or Tamil or any other Indian languages, you used to get a lot of hallucinations, a lot of garbage out. Slowly it starts moving better and better, partially because tokenizers also get upgraded. So now let's start talking a little bit about the output side of these models also, and then once that discussion happens, we'll leave a little break for questions. So say you are, as a user, right, now playing with these LLMs, right, the generation of the outputs, the terminology that is used is decoding, right. So decoding means fundamentally it is the as we said, language models, large language models are fundamentally decoder only models, and the process of iteratively pushing the output, taking it as part of the input and pushing the next output token and so on and so forth. That is what the term decoding means. So now remember one more thing before I exit out of this tokenizer discussion. Now the units, right, the model represents in its softmax label output side is going to be the tokens, right. So the number of tokens you have is exactly your size of your last layer of your transformer model, right. So if it is 50,000 then you are dealing with 50,000 output sized vocabulary or token space, right. So now let's get back to this output generation discussion. So the output generation discussion, suppose let us say for curiosity you ask this question to a large language model, right. So name an animal which is both domestic and wild. Suppose let us say this was your question, and the model now when it starts generating the tokens, right. So every token it generates, then it basically uses that as the input. Maybe the word cat had multiple sub tokens also or multiple tokens also to get generated. So we are not going down to that path. Assume that each one of them is a single token for our discussion right now. So suppose the model at the output had these 4 choices, right. So and then the probability was the highest for something like a cat. So if I choose to just take the max output, right, and the location of the max output in this case corresponds to the token cat, then I get the same answer every time, right. I keep asking the same question one more time, regenerate, I get the same answer because you are picking the top. I ask it to regenerate, it gives me the top. So, but that's not what we want when we ask a regenerate comment or question, right. You want different responses each time. If it is going to give the same answer, then you wouldn't even want to have a regenerate button there, right. So now what can we do? Again remember, we don't want, if let us say this question took you 5 seconds, if I click the regenerate button and it takes another 5 seconds, I am as a user going to be annoyed, right. We want it to be very fast. We don't want, it probably has all the 5 and it's showing me only one. As soon as I click it, I want the second one also, right. So that is basically the methods in the modeling world called sampling. So let us take the slightly abstract version of this input example that you said. Suppose I want to call the input as X, right. Maybe I should use a different color. Suppose I want to call the input as X, and suppose let us say the output is Y. So now what I said as argmax is what is called in the terminology of sampling and output generation called greedy decoding, right. So the term greedy means you are picking the maximum possible output, which would mean that you are picking, given the output at time instant t, you are picking at every instance the max over all possible tokens that are in the output probability side along with the input in the context, right. All the input in the context plus the previous output in the context goes in and the model generates a set of probabilities. You are just picking the top one. If I want to do more than this, right, now I want to basically take this entire probability as a distribution, a discrete distribution over the token space, right. I have, let us say, a set of tokens. We said 50,000 tokens as example. So I have 50,000 sized array, and each element of the array is one probability of that token being the output given whatever is the context, given the input plus the previous generation. I want to use that probability distribution that came out through the input transformer stack, and before that the tokenizer and all that processing has been done, and now you have this array. I just want to sample from this array of probability numbers more and more, not generate this array any further. Remember that generation of the array took all your compute, took all the parameters of billions of transformer layer weights and biases and other things in the tokenizer embedding matrix and whatnot, and you have reached this array, and now I want to just keep using this array to sample. Okay, so these can be from the output of the softmax, and in many cases you can also use the pre-softmax because even it lets you further be a bit more computationally frugal. So what is then sampling, right? So if you want to be again very simplistic for the case of this discussion, let us start with a case where you have only 4 tokens. Okay, assume that your space is just 4 variables or 4 tokens. In this case, these are what I call as the index 1, 2, 3 and 4, and one of them, right, for example, cat had the highest probability. Now let us assume that you place this 4 into in a cumulative distribution form, if you want me to use the probabilistic term for this, along the axis of 0 to 1, right. So you have a axis from 0 to 1, and the width of that particular entry is the probability of the index. So if I have, let us say, car, which is the first token, and this is the number 1 here, it occupies 10% of the whole real estate of 0 to 1, right. Now you have dog, which occupies 25% of the real estate of my total area of 0 to 1. As we want the cat being the token which has the highest probability, it occupies 60% of my real estate. So the overall space of 0 to 1 now got divided into chunks, each chunk having the width proportional to the probability that the model gave at the output of its inference, right. Now what you are going to do, you just generate a simple random number, a uniform random number between 0 to 1, call it u, and which of these buckets, which of these sub real estates that you created, where it falls, that is the class you are going to decide, right. So if I take u equal to 50.57, it lies in the bucket of the third entry, which means cat is going to be the output. Now you say regenerate. What do? I generate another random number. Now it became 0.32. Now I am going to put 0.32 in this real estate of 0 to 1. Suddenly the answer became dog, right. So every time you create a random number with a seed, and then when you say regenerate, another seed appears and another random number comes in the uniform distribution, and that random number gets placed into this set of possible outputs, and where it falls decides your output generation, right. So now you basically have from the same output distribution itself, simply by generating a new random number, you get a different response. But what it also follows is, as you can see, right, 60% of the times, if you have a uniform generator, 60% of the time on the average, you get cat as the response. 25% of the time you get dog as the response, and the rest it is lower in its probability of being an output. So this is what happens, you keep generating output, sometimes you get the same output because it was very high. Sometimes you get a different output because it was not so high that other output entries also became probable. Okay, hope this simple sampling itself is clear. It's not implemented this way, there are much more efficient ways to encode and implement it, but I just put it graphically so that it is relatively straightforward to follow. So now what happens? Now if I know that I can do it with a seed, I can do more things around it. I can do a lot more operations in the output array itself to feed it into this sampling process. For example, you say that I want to keep the top k. Top k means maybe I will say top 2. So in the previous example that you saw, top 2 would mean that I only keep cat and dog. Now what happens? My 0.6 and 0.25 has to get renormalized, right? The entire real estate is only the pink and the green in this color. So now pink expands, green expands, so that now they occupy the 0 to 1, and within the 0 to 1 now 0.6 would become maybe 0.65, 0.67 or so, and 0.25 would become 0.3 or 0.32, and now that is the two options you have. You don't even have an option to generate a quantum or a car, right, because they simply were not part of the top k. So you only pick the top k. Again, what you can do this before the softmax, because the softmax is a monotonic operation. You don't have to waste normalizing over a 50,000 array. You just pick the top 2 or top 5 or top 10 and just normalize those, which is much faster than normalizing a 50,000 sized array. You can perform now a k multinomial distribution, right? You don't have to have the vocabulary sized multinomial distribution to sample from. Sampling is also incredibly faster, right? This is very, very commonly used. A second option exists, which is called the nucleus sampling. What do? You don't try to do k, but you try to keep accumulating till you reach a threshold. Say I put a threshold of 0.8. What that would mean is I need to accumulate entries till I reach a possible value of 0.8. So this would require you to do a pre-softmax. It would require you to have softmax outputs. Now what happens? You say, I want to keep summing the top one, the next one above, below that, the next one below that, till I reach the threshold that I have set. A threshold is a number between 0 and 1, and you, as soon as you reach that threshold, you stop your number as p. So in this case, let us say if you put the threshold as 0.8, again you are picking the cat and the dog and you are ignoring all the rest. If you start putting 0.95, right, if you say 0.95 is my threshold, then what will happen? All these three will get part of it. If you keep it as 0.97, then you start saying all 4 of them will become part of your output. So again, you can see, do you want to have all the varied responses, or do you want to keep a threshold that is conservative, meaning you keep it as a very easy threshold so that only the top 1 or top 2 qualifies. So by moderating this p, you can again control how much varied your response is, right? Think of it, right? You ask the question, name an animal, and the model says quantum, right? That can be as wild as it gets, right? So it now starts having these wild responses if you keep a very large nucleus or threshold. Okay, so now you can also do, after you get this, you can renormalize it again. So if you keep 0.8, you got the top 2, you renormalize it, now you sample from only those. Right? Hope everybody is on board with the sampling strategy. The last one I want to do, also perhaps one of the most important ones, is to combine this with something called a temperature. Again, a very simple strategy but very effective, which is that, let's say the Zi here, I forgot to mention the notation here, the Zi is the before the softmax, right, pre-softmax outputs. So if you have Zi's as the pre-softmax output, and if I put just say t equal to 1, that is essentially your softmax equation. But instead of putting Zi directly, I scale it with, or I divide it by a positive number t, right? And t equal to 1 is the normal softmax, and anything that changes from 1 to above 1 or below 1 gives you different output sampling. So what happens again? When I basically change t, remember that, let us keep t to be less than 1, then you are pushing the number Zi, right? T is less than 1, you are pushing the number Zi, so the max further gets accentuated, means that the softmax becomes more and more peaky. When t is greater than 1, the model starts outputting more uniform responses. If you want a quick example, let us say if you had a pre-softmax output for these 3 outputs as 5, 4 and 1, at t equal to 1, you have e power, the final probability is proportional to e power 5, e power 4 and e power 1. So those numbers are listed here, 148, 54, 22.7, etc. But when you put t equal to 2, you have brought the numbers significantly down, and more importantly, what I want you to see is the relative values of the numbers got closer. When the relative values get closer, what happens? The distribution becomes more and more uniform. The extreme case is when you push t more and more to infinity, then you get everything equal. All the outputs become equal, means that you can sample anything out of the model. It can be any sequence of tokens that come out. To summarize this behavior, when you set the temperature, more randomness, more diversity is what you want, then you set the temperature high. When you want things to be factual, when I want to ask what is the capital of Karnataka, I don't want to have randomness, right? I want to set the temperature low, right? And when you set the temperature, sometimes the model can generate even contradictory behavior, right? Certainly when you ask, what is the capital of Karnataka, sometimes it can even answer Hyderabad, right? So then what happens? You start worrying that there is too much randomness, there is too much sensitivity to the regeneration, which is possibly because your temperature is low. Okay. Sorry, the temperature is high, right? When you keep temperature high, you are getting more and more random, incoherent behavior. But in some cases, it is actually good to keep the temperature high. Suppose I want to take a model and start saying that generate a poem about Bangalore's weather today or Bangalore's traffic today, right? If I want to generate a poem about Bangalore's traffic, then you might want to have a high temperature so that you get very varied, very interesting connections, right? So in social media, I was reading the formation of Karnataka, and where they said that this links to the Hindu mythology, and there itself they said that the mythology said this place was cursed by Karna. So which is also the reason why the traffic continues to be woeful, was one of the social media comments, right? So I started reading it. I never really connected to the traffic until the last sentence, right? So it is as creative as you can think of, that you read a mythology and at the end of it says is very true even today. That sort of a post you can generate by being creative with high temperature. But remember again, if you are in a domain, right, and you know, for example, a math, for example, a code output, you don't want randomness, you don't want diversity, you want the exact answer. So you want to be very precise, means a low temperature. Okay, so just this summary slide, and we will open up for some questions. What we just took the last 45 minutes or so on is on tokens, how you can derive them in a data-driven way, how the model is ingesting these tokens as fixed length vocabulary, and an embedding matrix is also part of it, which converts these tokens to real inputs to the transformer stack. We spent a little bit of time on the output side too, on the sampling, on temperature based sampling, on top K, nucleus based sampling, or a combination of this, right? You can apply a temperature, then apply a nucleus. So then what happens? Your nucleus also includes more, right? Remember that if I want to put a 0.8, but I kept a high temperature, then more candidates come inside 0.8. So you can also do a combination of temperature plus top P, and these are all very effectively used in sampling outputs from the model. So we'll take a short break. Thank you.